Great. So yes, we start now with the second talk of this session. It is by Alberto Salvio from University of Rome, and he will discuss quadratic gravity. So please.
Thank you very much. Thank to the organizers for organizing this workshop. It's very nice. So first slide is about first motivation for considering quadratic gravity. So quadratic gravity has a combination of r squared and r mu nu squared with coefficients alpha and beta. And these coefficients actually are unavoidably generated by matter loops, such as the one that is shown here. The double wavy lines are the gravitons. This is dictated by the renormalization group, as shown here in the RGs of alpha and beta. And I'm also including the effect of non-minimal couplings, psi AB, between the scalars present unavoidably in the theory phi A and the Ricci scalar, which is, by the way, also unavoidably generated by matter loops. If we also consider the dynamics of gravity, Stella in 1977 proved that the theory is renormalizable. The intuitive reason is that in the UV, the theory is actually the most general dimensionless one. And so you can reabsorb all the divergences in the counter terms. Here I'm also including, besides the R squared term and the W squared term, the Einstein-Hilbert piece plus a cosmological constant, which is necessary to have a viable low energy theory, and a matter piece, Lm. I'm also changing a little bit the notation with respect to John Stokes, because he called psi, I think the parameter below W squared, I call it F2, just to make the contact with my papers. I also wanted to stress that it's also possible to generate scales dynamically. These scales are the Planck scale, the cosmological constant, and the electroweak scale. And in this case, we call this theory a gravity, a dimensional gravity. Okay. Another motivation for considering this theory is the fact that the Higgs mass can be naturally much smaller than the Planck mass in this theory. And by naturally, I mean what Gerard 't Hooft proposed: the physical quantity is naturally small when setting it to 0 leads to enhanced symmetry. And in this case, we can compute the contribution to the Higgs mass in the theory, and it goes like the Higgs mass squared goes like the Planck squared times the fourth power of F2, or some combination of F0 and the non-minimal coupling of the Higgs. So requiring naturalness, we get a very, very small coupling of actually the graviton, as we will discuss later on. F2 has to be not exceeding 10 to the minus 8. Actually, this is a particular realization of presumably more general scenario that we call Softnet gravity. The idea is that maybe Einstein gravity is a good description only up to some energy which is intermediate between the electroweak and the Planck scale, and after that gravity gets softnet, becomes very, very weak. Okay, and in this case the Higgs mass gets a contribution which is small enough to be natural if this intermediate scale lambda g is not exceeding 10 to the 11 GeV, roughly speaking. So the reason is that for such small couplings, the Higgs field acquires some approximate shift symmetry that protects MH. Still, the cosmological constant lambda is not naturally equal to the observed value. So apparently, we haven't found the solution to the cosmological constant problem. And so maybe the only possible way to address the cosmological constant problem is to use the entropic principle and to introduce a multiverse in this field theory scenario. Okay, so now the Ostrogoski theorem that states that Lagrangians that depend non-degenerately on the second derivatives have Hamiltonians unbounded from below. This is the case in quadratic gravity at the classical level. So the way we see it is, for example, just by looking at the degrees of freedom around Minkowski space, which are the massless graviton a scalar omega with a square mass given by this formula, and a massive spin-2 field with some abnormal sign kinetic term. So what is sometimes called a ghost, and a squared mass m2 squared given by this formula. So this is the way the Ostrogoski theorem manifests in this particular theory. And by linearizing the theory, one finds a Hamiltonian for the degrees of freedom that has a piece, at least in the spin-2 sector, which is corresponding to the graviton, and another one which gives you the Hamiltonian of the ghost, which has a minus sign. So this minus sign corresponds to the Ostrogoski theorem. So how to deal with this problem? So have a proposal which is, for the time being, intrinsically perturbative. Perturbative because I split the metric in some classical metric and some quantum fluctuations. And the classical part, G classical, is solving the classical equations of motion, and this H hat is a quantum deviation. So let's start with the classical theory and see if we can deal with this problem. So essentially the problem is how to avoid the Ostrogradsky stabilities that are suggested by the theorem, because the Hamiltonian is not bounded from below. And the idea is essentially to see if we can have a metastable situation where the runaways can be avoided if somehow the energies are small enough. So first of all, recall that in the free field limit, this minus sign is not pathological. It doesn't give you any runaway because the decoupled ghost does not suffer from instabilities. On the other hand, effective field theory arguments tells us that at energies below the mass of the spin-2 massive state, we should not find runaways, even if this abnormal graviton has an order 1 coupling. Okay. Therefore, for intermediate values of F2 between 0 and 1, we must have intermediate energy thresholds between infinity and M2. So this means that the weak coupling case, which is F2 much smaller than 1, which is compatible, by the way, with Higgs naturalness, as we have seen, must have an energy threshold much larger than M2, okay, because it has to go to infinity in the F2 going to 0 limit. So this also tells us that we could see the effect of the abnormal graviton without runaways, essentially. And this argument can be made precise in classical quadratic gravity, such that the whole cosmology can only involve energies below this threshold and avoid runaways. So we have this metastability in classical quadratic gravity. I pointed out this in 2019. There was also a more recent paper by Dorais, Shapiro, and Shapiro, another Shapiro in 2019, and the paper by Alessandro Strumi and collaborators in 2020 that was posted by Alessandro earlier. Okay, so essentially what happens in quadratic gravity? What are these threshold energies? So, but by the way, these energies are basically they are not really energies because these quantities are not corresponds to conserved quantities, but they are something that have dimensions of mass. This is important. And these thresholds are this E2, which corresponds to the derivatives of spin-2 fields. Okay, so it applies to the boundary conditions because it does not correspond to a conserved quantity. And analogously, one can show that the energy E in the matter sector must satisfy an analogous condition, which is E much smaller than EM. Okay, so the important thing to notice here is that E2 is proportional to the Planck mass with the square root of F2, while EM is proportional to the Planck mass with the square fourth root of F2. Okay, so basically when F2 is much smaller than 1, this E2 is much smaller than M Planck, but it can be much bigger than M2. So you have a range of energies for which you can see the effect of the abnormal graviton without triggering the instabilities. There is also a very nice relation with chaotic inflation, the idea by Linde. First of all, for a natural Higgs mass, these two threshold energies, E2 and EM, are very, very high. So basically, we can only probe these energies by looking at the inflationary setups, inflationary observables. Okay. Another important thing to notice is that the ghost is completely inactive in the Friedman-Robertson-Walker metric. So only perturbations that break homogeneity and or isotropy may destabilize the universe. Okay, so these effects are basically deviations from FRW metrics. But we live in one of those patches where the energy scales of inhomogeneities that are called EI and anisotropies E were small enough. How small? This is given by these inequalities. And the reason why these inequalities are usually imposed is because these conditions justify the use of homogeneous and isotropic solutions to describe the classical part of inflation. But basically what happens, at least for F2, this order of magnitude, so really close to the critical value for Higgs naturalness, is that these inequalities imply also that the condition to avoid runaways that I've shown you in the previous slide are satisfied. And also the other way around. So the fatal runaways above these energy thresholds give some anthropic rationale for homogeneous and isotropic universe. When these are not satisfied, then we trigger the instabilities. And I verified this statement for several inflationary models like Starobinsky inflation, hilltop inflation, natural inflation, Higgs inflation, and others. Still have to find a model that does not fulfill this condition. Okay, so now let's go back to the splitting of the metric and address the quantum issues, because we can still have problems in the quantum theory, because fluctuations would lead to a tunneling through these energy thresholds, essentially. And the question is whether we can address this problem with a different quantization. Actually, with the standard quantization, I didn't find any solution. We didn't find any solution. But maybe there is a way to have a complete theory of quantum gravity by changing the quantization. Okay. So this is a situation similar to Dirac fermions that have a classical theory that is not stable because the energy is not bounded from below, but we can make it meaningful by quantizing the theory appropriately. In this case, we can make gravity renormalizable, but we have to introduce an indefinite metric, essentially, with respect to which the position and momentum operators are self-adjoint. But notice that probably this is my only comment about non-local theories, is the fact that even in non-local theories, if they respect standard axioms of quantum mechanics and relativity, they also have to secretly have an indefinite metric, because this is implied by Cullen-Lemma representation. A propagator cannot go faster than 1 over p squared for high momentum unless there is an indefinite metric. So the indefinite metric leads to the question, how can we define probabilities consistently? So this question is relevant also for non-local theories. So I have an approach for this. First, define an observable in a slightly different way than in normal quantum mechanics. The observable is an operator with a complete set of eigenstates. So for any state, I can decompose, for any state psi, I can consider this decomposition for Ca and some complex numbers. And also, it's important to notice that one can show that the basic operators, the field, the momentum, conjugate momenta, and the Hamiltonian have a complete eigenstates, so it can be observable with this definition. We interpret A as a state where the observable assumes certainly the value A. And then we basically think as an experimentalist. So we prepare the system a large number of times. We define the state of the complete system as the direct product of the single states, psi. And then we define a frequency operator, Fa, which counts the number Na of times there is the value A in the state A1, An of the basis, which is defined therefore like this. So the crucial point now is to notice that in the limit in which n goes to infinity, this psi n becomes an eigenstate of the frequency operator with eigenvalue precisely given by the Born rule. Okay, so this implies, in particular, that the probabilities are positive and they sum up to 1 at any time. So the theory is unitary. So what happens to the way we express the Born rule in terms of, let's say, matrix elements? Basically, there is a set of emergent norms to compute the probabilities, which are defined by this relation. So A prime PA, defined like the Kronecker delta. And this applies a positive norm in the Hilbert space, like I show in the equation below. And so in this case, we can express BA, the Born rule probabilities, in terms of these positive norms, not in terms of the indefinite norm that I mentioned before. Okay. Then there is another non-standard aspect of the quantum theory, in addition to what I've just said, which is the fact that the Dirac-Pauli quantization of canonical variables have to be used. What is this Dirac-Pauli quantization? Basically, from what I said before, any observable can be split in some Hermitian and some anti-Hermitian part. So there are observables that have real spectrum, and others possibly that have imaginary spectrum. So in normal quantum mechanics, which is the case basically for energies below the mass m2, we only have the first possibility, but in general, we can also have observables that have an imaginary spectrum. And this has to be the case in quadratic gravity for the canonical coordinates of the abnormal graviton. Because of the Hamiltonian like this can have a spectrum bounded from below and at the same time normalizable eigenfunctions only if we choose this possibility. Then another question now is what happens above M Planck. So we have a theory which is basically having two parameters at high energy. One is F2, another one is F0. And F2 is asymptotically free for F2 squared positive, and there is no problem with F2 squared positive. But F0 squared is asymptotically free only for F0 squared negative. And F0 squared negative corresponds to a tachyon, a scalar tachyon. However, Alessandro and I showed in 2017 that when F0 goes to infinity in the infinite energy limit, F0 does not hit any Landau pole, provided that all scalars have asymptotically value invariant couplings, which means that psi AB has to be equal to this value, and all other couplings approach fixed points. Okay, so this is essentially asymptotic safety. And in this case, quadratic gravity can flow through a value invariant theory, also known as conformal gravity at infinite energy. A possibility is that basically there is at observable energies F0 and 1 over F0 and 1 plus 6 psi, where psi is a generic non-minimal coupling, are both very small. And in this case, lambda g, the Softnet gravity scale, is equal to m2, the mass of the abnormal graviton. Another possibility is that F0 to the -1 and 1 plus 6 psi are large at observable energies. And in this case, lambda g is equal to the maximum between m0 and m2. There is also a nice thing to say about the initial time cosmological singularity. Since quadratic gravity flows to conformal gravity in this scenario, in the UV, and the FRW metric is conformally flat, the initial time cosmological singularity of GR can be avoided. So now let's go to the inflationary observables. So there is no difference compared to GR for M2 greater than the Hubble rate during inflation, H. while for M2 smaller than H, there are two basic modifications. One is the tensor to scalar ratio R gets suppressed in the way I showed here, where RE is the tensor to scalar ratio in Einstein gravity. And this is interesting because models that are excluded for a large RE, like quadratic inflation, become viable in this case. Another interesting aspect is that there is an isocurvature mode which fulfills the observational bounds, at least for the inflationary models that I mentioned before and others. And this corresponds to the scalar component of the abnormal graviton. So this plot shows the compatibility of this isocurvature mode with the Planck results published in 2018. So these are the most recent results. Basically, these dashed red lines correspond to the Planck bounds. And this plot shows that for essentially RE smaller than 0.01, the models are allowed. So the bound is weaker than the one in Einstein gravity. So models that are excluded in Einstein gravity because they have a too large RE can become viable in this theory. Another part of my talk regards ultracompact objects in this theory. So the theory is of gravity is very weak above lambda g. So what happens to ultracompact objects? Basically, there is a linearization mechanism. When the Schwarzschild radius RH, which is 2GNM, satisfies this bound, RH much smaller than 1 over lambda g, we can describe analytically ultracompact objects, basically because the linear theory holds in this regime. And there is also another talk by Bob Holdom in this conference, which we discuss about the case RH greater than 1 over lambda g. So in order to understand the linearization mechanism in more detail, here I mentioned the case of a point mass for which the energy momentum tensor is equal by this expression. And notice that in this case, the trace of the energy momentum tensor is not 0. And so lambda g is equal to the maximum between M0 and M2. Okay, so in this case, what happens? This source generates a Newtonian potential, which is given by this expression. And one can note by some simple algebra that the modulus of the Newtonian potential is smaller than this combination of RH times M2 and RH times M0. So for RH much smaller than the minimum between 1 over M0 and 1 over M2, the potential should be small, and a horizon does not form even for an ultracompact object. So for a compact object that is a black hole in GR. Another important thing to notice is that in this theory, singular delta function sources generate a singular response. But this is not a pathology of the theory, because this is the case also in even asymptotically free EM-Mills theories. If you put a singular source, you get a singular response. Like essentially, technically this emerges just because as a delta function source in electrodynamics generates a Coulomb potential which is singular at the origin. However, the argument that I've just said can be extended easily to general sources and spacetimes that are regular everywhere. So spacetimes of this general form, there is a coefficient A in front of the time component, coefficient B dividing the R squared, and some generic energy momentum tensor with an energy density rho and some pressures. Okay, here I show you the general technique to proceed. Maybe I can skip this. It's a quite technical slide. And here I give you the example of a ball of constant density rho, R, and a mass M. So we can compute the A and B through the formula that I showed you before. And these plots show several properties of this solution. For example, the first plot on the left, upper left, shows you that A and B are different from the Schwarzschild solution. The second plot, upper right, shows you that the pressure and density are positive. And the plots on the bottom show you that the curvature invariants, including the y-squared term, are finite even at the origin. Okay, so these plots also show you that the linearization mechanism takes place because we are comparing essentially the linear theory with the nonlinear solutions, and we are finding a very good agreement between the two. So the linearization mechanism holds. And finally, here I also show you what is the condition on the parameters of the theory in order to have these ultracompact objects that are also stable with respect to Ostrogradsky instabilities. Essentially, M2 has to be much smaller than this capital R divided by RH times the Planck scale. So for M2, that corresponds to a natural Higgs mass, there is a lot of parameter space for which this is true. Another plus of the linearization mechanism is the fact that the absence of microscopic black holes is a good news for the Higgs vacuum instability, because a black hole with RH smaller than 1 over H max, where H max is the value of the Higgs field for which the effective Higgs potential acquires its maximum, is very dangerous for the standard model, as it can induce electroweak vacuum decay. And this type of black holes can be avoided in this theory because we have just seen that microscopic black holes below a certain scale should not form because of the softening of gravity. Furthermore, if ultracompact objects are stable, they can also be dark matter. There's also a paper, more recent paper by Bob Haldeman collaborators about this. So presumably he will talk about this in his talk too. Okay, so how many minutes do I have?
3 minutes.
Oh, 3 minutes. So maybe I can briefly discuss the implications for Bsm phenomenology. So given that gravity is now UV complete, it makes sense to look for relativistic field theory theories that hold up to infinite energies. So still there is an issue about the non-perturbative formulation, but we can at least hope that this can be solved in the future. And there are essentially two options. One is that all couplings flow to zero at infinite energy. So we have total asymptotic freedom. And another one is that some of the couplings flow to an interactive UV fixed point, while the other ones flow to zero. But this option typically requires non-perturbative methods. Essentially, the second option is the asymptotic safety for matter fields. Okay, this slide tells you also that we have to avoid U1 gauge factors in this case. So we have an explanation of the electric charge quantization, and we found two options that are not severely constrained by proton decay, which is Patti-Salam and trinification, which leads to some new physics at some high energy scale. Okay, so going back to the conclusions. So quadratic gravity is a UV complete gravity theory. The classical runaway solutions can be avoided even at energies exceeding the ghost mass, M2, and the runaways occurring above an energy threshold, which is much bigger than M2, can explain homogeneity and isotropy for F2 of order 10 to the minus 8, which is the value suggested by the Higgs mass naturalness. Interpreting probabilities as emergent from repeated experiments leads us to a way of quantizing the theory where all probabilities are positive and they sum up to 1. And there is also another non-standard aspect of the quantum theory that has to be included, which is this Dirac-Pauli quantization of some of the canonical variables. And furthermore, for F2 of order 10 to the minus 8, which is the maximum value compatible with the Higgs mass naturalness, quadratic gravity leads to testable predictions for the inflationary observables. And ultracompact objects are eventually horizonless. This is also a prediction of generic Softnet gravity theory. So this goes beyond quadratic gravity. And still there are issues of these theories. I think one thing is the fact that we lack, for the time being, I'm working on this, but we lack for the time being a complete non-perturbative formulation. And also there's no apparent way apart from the entropic principle of addressing the cosmological constant problem. Okay, thank you very much for your attention.
Thanks, Alberto, for this nice talk. Okay, so I see already that there are several questions. So the first one was by Luca, who wrote it in the...
Okay. So yeah, I can speak. Okay, thank you very much, Alberto. And actually, thank you also for showing the picture of Ostrogasky. It's the first time I see his face. So okay, so I have a question regarding on the last part when you spoke about horizonless objects. Okay, so just to clarify, maybe you partly give the answer after, but after I wrote the question in the chat. So is your approach? So, I mean, is your claim that you never hit any strong carbon regime your approach, and so you can avoid black hole production up to some scale?
So my claim is that the solid claim is that for, let me find the slide again. Okay, so when RH, where RH is the Schwarzschild radius in Einstein theory, so is 2 Newton constant times the mass of the object, is much smaller than 1 over lambda g, where lambda g is the Softnet gravity scale, then the horizon does not form.
Okay, so it's like some kind of mini black hole. So, I mean, you avoid, I mean, some kind of...
basically, it's not, no, it's not. It's not a black hole.
Yeah, so you avoid mini black holes, let's say, right? Because anyway, you have some critical...
You avoid the microscopic black hole. So take into account that this lambda g is of order, typically of order 10 to the 10, 10 to the 11 GeV. So...
Okay.
So these are really microscopic. And so what I expect is that the theory does not have really objects with the horizons, even at the macroscopic level, but I cannot prove this.
Yeah, because I mean,
so maybe there are, but I expect that horizon does not form.
Because I mean, usually, at least black hole solution like Schwarzschild, no, the mass is always. I mean, the mass in the case of Schwarzschild is a free parameter. Okay, so it can be really, in principle, of any mass a black hole. Okay, so it's just an integration constant. But when we, let's say, try to avoid the horizon, we anyway introduce some critical scale. So I don't know if it can be really true for any mass unless this critical scale can all. I mean, if you increase the mass, this critical scale should be mass dependent and should change at the same time with the mass, okay, in such a way that this inequality is always, for instance, satisfied, okay. Otherwise, I don't see how you can always have an inequality for this like Schwarzschild radius less than something. Just because,
so So this is the RH in Einstein theory.
Yeah.
So.
So I think this is this looks like a longer discussion, so it's better suited for the discussion session. Okay. And I would take just one more quick question since we are running out of time. And so the next was Shravan.
Hi. So you take this F2 to be 10 to the power of -8, right? What is the corresponding value of M2? I mean, what is the value of M2 you have in your theory?
I cannot understand you. Can you repeat it?
I'm saying, what is the value of M2? I mean, the additional massive graviton mass.
So M2 generically is equal to F2 times M Planck with some square root of 2. So it depends on F2, but if F2 is taken to be 10 to the -8, then M2 is around 10 to the 10 GeV.
So it's around the 10 power 10 GeV. Okay, it's around the mass of the inflaton, right? No.
Yes. So okay. So this is important for inflation because in these inflationary models that I mentioned, the inflationary scale is around 10 to the 13 GeV. So if you take F2 10 to the minus 8, then you can have M2 below H during inflation. And then rapidly reheating takes place and H goes below M2.
And there is no problem due to this mode at the end of inflation because it is unstable mode, right?
So this is the, so I have some slides about this. So I took the example of Starobinsky inflation. And so basically, so these are some background slides. So you're asking about inflation. So, okay, so this one. So I made some explicit nonlinear calculations for Starobinsky inflation. And so you have to fix the model, of course, to do explicit nonlinear calculations. And here I'm considering also some deviation from the FRW metric because I said it is needed. And essentially what happens is that if you fix the initial conditions, so more generally the boundary conditions of these fields to be satisfying these bounds that I showed you before in terms of E2 and EM, I don't know if you remember, then the anisotropy quickly goes to 0 and one recovers the GR behavior, as I checked explicitly in the numerical calculations. So you start from a very large perturbation with respect to M2, which is very small with respect to E2 and EM, and quickly you approach the FRW metric without so you avoid the runaways.
Yeah, during inflation, fine. But what about the end of inflation? Because M2 will play a significant role, right? During inflation, I understand.
Yes, and
it's
after
not clear
inflation.
to me.
So,
yeah, after inflation.
After inflation, the Hubble rate decreases very rapidly, and then it goes below M2. When it goes below M2, the W square term does not affect the cosmological observables.
Yeah, but you will have some intermediate regime where you will be trouble, right?
But you mean you're speaking about the perturbations?
Yeah.
Okay, so basically the perturbations here, for the perturbations, I treat the dynamical degrees of freedom with the quantum prescriptions that I showed you before. So I have to introduce these new aspects of the quantum theory, which includes these positive norms and this Dirac quantization to do the calculations. And at the end, these are compatible with the probabilities being positive and the sum of the probabilities is equal to 1. And also they are compatible with the positive power spectra, because essentially there's a cancellation between minus signs that leads to positive power spectra. If you apply precisely the quantization procedure that I showed you before.
Okay, so I would suggest that we close for now the discussion, and we can come back to the questions of Richard, Anupam, and Alessandro later during the discussion session. So I would suggest that now we thank Alberto again for his nice talk.
Thank you very much.
And the next speaker now is Gia Vali. Gia, are you there?
Hi, can you hear me?
Hi, yes.
Okay, yeah.
So
I need to share my screen, right?
Yes, but I think Alberto first has to stop sharing.
Yes,
it should be on the top. Stop the